Welcome to our third prerequisite video for calculus, and our topic today is logarithms. Logarithms are important and they are definitely something that students seem to struggle with the most, and so I want to make a quick video today and kind of breaking down logarithms and showing actually just how simple they really are. So we're going to start with just a quick review of exponents, talk about what a logarithm actually is and do some examples, explore the properties of logarithms, and then real quick graphically show the relationship between exponential and logarithmic functions. So in order to understand logarithms, we have to first make sure that we're pretty solid with exponents. And so we say that this is b to the x equals a. That means that we'd multiply b by itself x times and get out a. I call this b because b is the base, x is the exponent, and I'm just going to say a is like the answer. Books will write this a little bit differently, but most often this is b because it is the base. Let's start with a few very simple ones. We have 3 to the first, which we clearly know is 3. I'll just put the answer beneath. 3 squared, which we know is 3 times 3. And 3 cubed, 3 times 3 times 3, which is 27. Now, if we look across these blue numbers that I have down here, we can see that this is 3 one time, right? This is 3 two times, 3 times 3. And this is 3 three times, 3 times 3 times 3. But if we move across here, we see the pattern is times 3 because there's one more 3 every single time. So if you needed to find 3 to the fourth, you could take 27 times 3. And we could keep repeating that pattern. But I do want to go the other way. If we look to the left, naturally the next value would be 3 to the 0. And so if we go left, instead of multiplying by 3 to get to the next one to the right, we are dividing by 3. So if we divide by 3, if we take 3 and divide it by 3, we'll get 1. And that is one kind of pattern way of showing that anything to the 0 power actually is 1. Then we can actually continue our pattern. To the left here, I would take 3 to the negative first, 3 to the negative second, and 3 to the negative third. Yes, we can have negative exponents. Let's continue our pattern. We divide by 3 to get each next value here, next answer. And if we divide 1 by 3, we'll get 1/3. And then if we divide this by 3, aka multiply the denominator by 3, right, multiply, we will get 1/9. And if we divide 1/9 by 3 or multiply it by 1/3, we'll get 1/27. And so again, you can see a lot here in the way of patterns. When we do have negative exponents, and this is something I've seen students struggle with quite a bit, negative exponents do not give us negative solutions. We raised 3 to the negative third, negative second. We didn't get negative answers. In fact, you won't ever get a negative answer with any type of exponent. So let's see what happens when we have a negative exponent. What we did was we flipped it. Check it out. 3 to the third is 27, but 3 to the negative third is 1/27. We flipped it. So the rule is if we have some base and it's to a negative exponent, that look a little better, that is the same as 1/, that base to that positive version of that exponent. We know that 3 to the second is 9. 3 to the negative second is 1/3 to the second, or 1/9. Here are some practice problems for you to try. Once you have them written down, go ahead and pause the video, figure them out, and then press play to check your work. The first one's pretty simple. Number 2 practices the negative exponent rule we just talked about. And number 3 was a little bit more challenging, but we understand that, hey, we're taking 1/2 to the 5th power. That means multiply 1/2 by itself, 5 times. But what we really see is the numerator becomes 1 to the 5th, which is just 1, and the denominator becomes 2 to the 5th, which is 32. So the rule of thumb, when you have fractions raised to a power, you raise the numerator to that power and the denominator to that power. That's it. If you're unconvinced, you can always write it out and see what the final answer will be. The next main idea in exponents is when we have what I call fractional exponents. A lot of books will call these rational exponents. but I like to call them fractional. They're the same thing. All right, so if we take a base to m over n a lot of times is 1, right? But if it's not 1, then we have to worry about this. So I want you to write this down, make sure you have it written down, and then we'll explore a few examples and show with some numbers how it really does make sense. Okay, in this first example, we're taking 64 and raising it to the 2/3 power. I don't know how to multiply 64 by itself, 2/3 of itself. That's confusing. So we're going to use this rule for fractional exponents. And what we can do is decide which rule to use. So I'm going to write them both out. Let's realize that our m value is 2 and our n value is 3. So the 3 goes out here in front of the root. That's actually called the index. It's what kind of root we're taking. And in this case, we're taking a cube root because this value is 3. So we have a 3 there. I'll get one that I like. There we go. And then in this first case, we can put this m value, this 2 value, right next to the 64. Or we can choose to write it again as a cube root, but we can write the squared on the outside, which shows that we're technically doing this thing first. If you want to put parentheses up here at the top one, you can too. This is just showing that we can do these in either order. What would you rather do? Would you rather first square 64 and then take the cube root? Or would you rather first take the cube root of 64 and then square it? I'm going to go with this one. I don't know what 64 squared is and I don't have a calculator on me right now. But I do know what the cube root of 64 is. So I'll put a little equal sign. The cube root of 64 is 4. And so then we're squaring 4. I don't really still need those parentheses. And we'll get 16. That's our final answer. Now, if you did 64 squared and then took the cube root, you would in fact still get to the value of 16 in the end. It just is giving you, two options to see whatever one is simpler to do first. Let's try another one. All right, getting a little bit crazy here. We have a negative fraction as our exponent. Oh my. So what we know is that we can write this using our negative exponent rule. It's 1 over 32 to the positive 2/5. Cool. That's all it is. So negative exponents, it's just 1 over. Remember, we said the rule was to flip 1 over, and then it's positive. All right, so we know how to deal with 32 to the 2/5. Basically, we have to take the 5th root, and we can do that with 32. So once again, we're going to choose to use this one instead because it's easier to take the 5th root of 32 first rather than square 32 first. So this is the 5th root of 32, and then it gets squared. Now you do not need these parentheses. I can write this 2 out here just like that. Now again, I could have written the 2 on the inside here, but I don't feel like squaring 32 and then taking a 5th root. It's much easier to do the 5th root first. The 5th root of 32 is 2. And then we have to square that value. So we're left with 1/4. So in the beginning, if this 2/5 was positive, our answer would just be 4. But since the 2/5, the exponent was negative, we had to do 1 over. And so all of our stuff that we were working on ended up in the denominator because of the negative exponent. All right, go ahead and write this one down and simplify it. Pause the video and then press play to check your work. Okay, we had 25 to the 3/2. That means we have the square root, 2 is our index, of 25 cubed. Note that we do not have to put a 2 here. There are certain things in math that we just don't write. If I just said x, you don't have to put a 1 in front of it. Same thing with a square root. We know that it's a square root, there's a 2 there. You don't have to put the 2. All right, so it's a square root of 25, and then that gets cubed. It's much easier to take the square root of 25 first rather than cube 25. Then we get 5. Cubed is 125. Now notice at the start, 3/2 is an exponent that's larger than 1. That means our final answer is going to be larger than our original base. In the other examples, we had exponents smaller than 1, and so our answer ended up smaller than our original base. Finally, we can move on to logs. The reason that we reviewed exponents so thoroughly is because to answer the question, what is a logarithm, we need to understand exponents. So what is a logarithm? Logarithms are a fancy way to write exponents. That's it. In fact, a logarithm is an exponent. Take a look. Remember before when we defined kind of what an exponent was? We said b to the x equals a. Well, an alternate way to write that is log base b of a equals x. Our log is the exponent. In fact, the form on the left is called exponential form, and this form, an alternative way to write the same thing, is called log or logarithmic form. Let's just do a simple exponential expression, or equation rather. Let's say 2 to the third is 8. Well, how do we write that in log form? The base is 2, so we'd say log base 2 of 8 is 3. The logarithm is the exponent. If you were to cover up this value of 3 and you just were asked to figure out what this equaled, you would think, what do I have to raise 2 to in order to get to 8? 3. Because a logarithm is an exponent. Okay, let's try another one. Let's do 16 to the 1/2. Let's figure out what that is. This means we're taking a square root, so that's 4. And then we'll raise 4 to the first, so we'll get just 4. So 1/2 power is a quick way to say a square root. All right, our base is 16, so it's log base 16 of 4 is the exponent. What did we have to raise 16 to in order to get to 4? 1/2 power. So the log base 16 of 4 is 1/2. All right, what about if we use the base of 10, the number system that we live in, basically use always. Let's say we have 10 to the 4th, and 10 to the 4th is just a 1 with 4 zeros, so it is 10,000. Now our base is 10, but I'm not going to write a base of 10. Instead, I'm just going to write this. How many zeros we got? One more. There we go. I'm going to write that that's 4. See, in math, like I gave the example that with a square root, we don't have to put a little 2 out in front because we assume it's a square root. Same thing with logs. If you don't see a base down here, you can assume that it's 10 because we are in the base 10 number system. So you could write a 10 down here, but it's unnecessary. So if you ever just see log with no base, there's really a base there. It's 10. Okay, another common number that we'll see a lot in calculus this year is the number e. If you'd like to read up on e, you totally can. It is not as famous as pi. Well, it's not as popular as pi, but it is just as important and famous as pi. There we go. E is a transcendental number. It is irrational, and it's about 2.718 ... It does go on forever. It's irrational. But anyway, it's another common base that we use because it's its own derivative when we use it as an exponential function, and we'll see that in the next few chapters. But if we are using e as a base, we're going to use a natural log, which we mentioned in the video prior. So we'll say natural log ln, and then much like we don't have to write 10 with log, we do not have to write e with natural log. So it's natural log, which automatically has base e, ln of 1, and that is 0. Because what do we have to raise e to in order to get 1? 0. Anything to the 0 power is 1. All right, next up, let's evaluate some logs. I'm going to draw a little thought bubble here because it helps us to kind of figure out, like, what do we have to think in order to evaluate this log. Remember, a log is an exponent, so I'm looking for what does this equal? I'm looking for the exponent. Well, the base is 4, and the answer is 2. So we're going to say, put this into exponential form. We're going to say 4 to the what is 2. Well, I have to get smaller, so I need to take the square root of 4 in order to get to 2. Therefore, the square root of 4, aka 4 to the 1/2, is 2. Therefore, log base 4 of 2 is 1/2. Let's try number 2. Log base 3 of 81. What's our thought process here? I'm looking for what is the exponent? A log is an exponent. So 3 to the what will give us 81. Well, I know 3 squared is 9, 3 cubed is 27, and 3 to the 4th is 81. Therefore, our answer is 4. All right, this one is natural log, but the thought process is still very similar. We're still looking for an exponent, except our base is e. So we're thinking e. So the base down here is e. I'm just going to kind of sketch it in real quick. It's kind of weird. Yes, there's 2 e's in this problem. So it's e to the what gives us e. Again, e is just a number. It's about 2.7. But e to the what will give us e? Well, e to the first will give us e. Any number to the first is just itself. So ln of e is 1. All right, let's look at number 4. Log base 5 of 1/125th. So let's think about our thought process here. What do we need to think? All right, our base is 5. So 5 to the what will give us 1/125. I do know that 5 to the 3rd gives us just regular 125. But since it's flipped, that means that that 3rd, had to have been negative. So 5 to the negative 3rd will give us 1/5 to the positive 3rd, or 1/125. Therefore, the answer to this is -3. One last thing I want to talk about with logs today and why exponents are so closely related to them. Not only that logs are exponents, but logarithmic and exponential functions are actually inverses of each other. And if you recall from previous classes, this is the line y equals x. And whenever you graph something, if that function has an inverse, meaning if the function is 1-to-1, if it passes both the vertical and horizontal line tests, then it will have an inverse, and an inverse is a reflection about the line y equals x. So you can clearly see that this blue graph, 2 to the x, and this red graph, log base 2 of x, are inverses of each other. They're flipped. If you notice, there's the coordinate point 1, 2 on the blue graph, and then if you flip x and y, the coordinate point 2, 1 is on the red graph. All right, so that's just a quick review of what inverse functions are. Let's just explore real quick why this works. This is pretty cool. So let's use this example. Let's use y equals 2 to the x. This is called an exponential function. That is because x is in the exponent. And it grows exponentially, as you can clearly see. And then as you plug in negatives, right, 2 to the -4th, 2 to the -5th, those are very small positive numbers, right, 1/16th, 1/32nd, like we learned earlier. Let's actually put what a few of those values are on there on a t-chart for this exponential function. All right, if we plug in, let's plug in like -2, -1, 0, 1, and 2. Just plug in those 5. So if we plug in -2, we'll have 2 to the -2nd, which is 1/2 to the 2nd, or 1/4. And 2 to the -1st would be 1/2 to the 1st, or 1/2. 2 to the 0 power is 1, 2 to the 1st is 2, and 2 to the 2nd is 4. And you can clearly see that those coordinate points are on this blue graph here. Cool. All right, let's find the inverse of this. So let's find the inverse of y equals 2 to the x. The way that we find an inverse function is we literally invert x and y. So I'll do this in black. So I'm going to invert x and y. So I'll now have x equals 2 to the y. All right, now from here, this is exponential form. We want to get this into logarithmic form. Well, I know that the base is 2. Therefore, we will have log base 2 of x equals our exponent y. Now we can just write that going the other way, and we'll have y equals log base 2 of x. So we can clearly see that this original exponential function, 2 to the x, has an inverse, and its inverse is log base 2 of x, which are graphed in the respective colors there. So I think that's pretty cool. Exponents and logs are extremely related, and their functions are actually inverses of one another. So I hope you had a good review of the basics of logs and a few reviews of different kinds of exponents and how to evaluate them. Thank you guys, and I will see you again soon.